Are you sure? Okay, hi, and welcome back, everybody. Okay, so that was the feature and representation learning. Do you all have a good intuition now how that feature and representation learning happens and why it happens? So what's driving this? What's driving this network to come up with these ghost faces and sort of like bigger ghost faces as you walk up? The labels, the error-based learning, exactly. Okay, and in some sense, this is hierarchical. Can you see that? Yeah. And how does this hierarchical stuff? What do you think? Why does this happen? Yeah, it's partly the architecture. If you look at the layers, like one layer always has sort of like only direct information from the previous layer. Yeah, and you can see that the middle layer, in some sense, the hidden layer too, is combining information like from these little edges, like these basic grammar pieces, and it's putting them together into sort of like larger face grammar things, and then layer 3, these ghost pictures and stuff like that. You can see this is really error-driven learning. It's like this backpropagation, just changing the plumbing or changing the weights, and it's coming from the architecture of the system. The how the system is configured, like in these layers and stuff like that. Yeah. Okay. So that's feature and representation learning, and that's one of the key ingredients of why neural networks can be so incredibly powerful. Okay. Now we talked about pictures. So what about language? Okay. So here's a translation example. Here's a translation from English into German, like, is everything okay? Alles paletti. Yeah. And so we could have, in theory, we could have lots of labeled training data, like machine translation, for example. If we had, like, I don't know, let's say we had 10 million sentences in English and 10 million sentences in German, and each of these pairs were translations of each other. Yeah. So what do we have to do in order to get the neural network learn language? Yeah. Okay. Yeah. Exactly. Yeah. Very good. Because it's all arrow driven. Yeah. And we may have some clue because kind of like, if the translation is wrong, maybe we can measure that, because this is labeled data. Yeah. It's supervised machine learning because for each English sentence, we have a good German translation. And if the network spits out something else, then we could define an error and use backpropagation. That's actually how it's done. Yeah. But what else do we have to do? What did we have to get? What did we have to do to the pictures to get them into the neural network? Yeah, the network has to have nonlinearity because, like, if it's a deep network and if we didn't have nonlinearity, it would just collapse into a flat linear function. Yeah, we have to have all these pairs, like, 10 million pairs, like, English sentence, German translation, English sentence, German translation. Yeah. Okay. Yep. Because the only thing, yeah, the only thing that these neural networks understand is numbers. And pictures, digital pictures, are naturally numbers. They're a vector of numbers. So yeah, so now what we have to do is we have to get the words into vectors. Okay. And that is sort of like very alien to a linguist, like, like, for example, to me. But of course, our colleagues in information retrieval and information extraction, of course, words are vectors to them. Have been for 70 years, 80 years. Like, they say, yeah, you linguists, kind of like, you're crazy. Words are vectors, nothing else. And I show you how, for them, it's totally normal. Also, library science. If you do library science, kind of like, of course, a word is a vector. That's how your catalogs are organized and how you search in libraries. A lot of IR and information extraction, information retrieval actually comes from library science. But anyways, we'll get there. So we have to get the words into vectors. Okay. And here, and also the outputs, kind of like so, because the only thing that can work as input for neural network is vectors, is numbers, and the only thing that can compute for output is a vector as well. Remember, if I have like these two outputs for cat neuron and doggy neuron, yeah, do you remember those two? That's a vector with dimensionality 2, where the first element in that vector is the cat output, and the second one is the doggy output. It's a vector. Yeah. And here, for example, the input is a vector, the output is a vector. Yeah. Here in that one, the input is a vector, the output is a vector. Remember, the output was like 1,000 people, 1,000 different neurons, and Auntie Sally was neuron number 32. Okay. And because of the supervised learning, I know that I want that to flare up if there's a picture of Auntie Sally. Yeah. Okay. So the input is a vector, the output is a vector. Okay. Yeah. And there was something else I wanted to say, but I forgot. Anyways. So we have to get the words into vectors. And so each word is a vector. So then the network, if we want to do machine translation or something else with language, like question answering systems or chatbots or something like this, it has to have very large inputs because, like, if each, like these vectors, they're often called word embeddings. And these word embeddings are often 128 dimensions or 256, or they're usually powers of 2 or 512 or 1024 or 2048 or like 4096 and stuff like that. So these have to have a lot of input neurons and a lot of output neurons. And we'll come to that. Yeah. But if we can get the words, if we can get words represented as vectors, then potentially we can do something with words and language in neural networks. Okay. So here, like the training data is easy. Like, this, for example, would be for machine translation, supervised training. I always have like an English sentence paired with a German sentence for an English-German, German-English machine translation system. And for this to work well, we need about, I don't know, 10 million, 20 million, 30 million, or 50 million or something like that sentence pairs. Yeah, but that's the data. And it's supervised because for each English sentence I have the German, the other way around. For each German sentence I also have the English. It's kind of like supervised in two directions, if you like. Yeah, it's the same as the doggy pictures with the labels and the cat pictures, where for each picture I either have a cat label, human label, and a dog label. And these translations were done by humans, by human professional, human translators. That's where the system would learn from. Okay, so how on earth do we get the words into vectors? And for each of the word, we have to have a vector. And that's kind of like the next part of the story, I think. Okay. So we want to get the words somehow as numbers into neural networks, and the vectors that we will come up with are going to be dense vectors. And dense vectors just means that the numbers you find in these vectors, they are floating point numbers. So 0.8576 minus 1.389, stuff like that. Then they're not integers, yeah, at the moment. So they're going to be floating point numbers. That's what it means dense, because you remember a vector describes a point in vector space, and a dense vector is a vector that can potentially define any point in that vector space. And if I just use integers, I can't do that. Now, the space would be digital with integers. The first dimension is 1, the second dimension is 1, and the third dimension is 1. But I could not go to that point over here. For that, I need rational numbers, real numbers, floating point numbers. Everybody with me? So that's what it means to have a dense vector. Okay. And ideally, we would like to do this in a way that words that are in some sense similar in meaning are close together in vector space. Okay, in this geometrical mapping of the words. And words that have very dissimilar meaning are far apart in the vector space. Okay, if we are able to succeed in this, then we have a nice notion about similarity. The closer words are in space, the more similar they are. So synonyms should be super close in vector space. Okay, and now compare things like, if you have this big question mark whether in human languages true synonymy exists. So many people would doubt that, but you have things that are pretty similar. If you have couch, settee, sofa, that's kind of like, yeah, okay, it's pretty close. But algebra and zebra are pretty kind of like, okay. So you want couch, settee, sofa, armchair, you want like clothes, maybe the days of the week, I don't know, whatever, kind of like one of the close in vector space, but you want zebra to be here and algebra over there. Algebra is probably with analysis and, I don't know, real numbers and weird stuff like that. And, yeah, and the zebra is with the cows and the elephants and, okay. All right. This is an example. This is what these vectors look like, the word embeddings. So these are 100-dimensional vectors for the two words time flies. That's what they look like. Okay. And we're going to get there, how I get them. Okay. So just for kind of like, yeah. Yeah. Very good question. So kind of like words can be polysemous. Yeah, so flies could be a verb, like, flying or something like this, or it could be like an insect or something like the word can could be like a modal auxiliary, and it could be like a can of beer, like a noun or something, Obama, yes, we can, and yeah, it's like, here, the way I'm going to do word embeddings is that's all conflated. Okay. So any word, no matter how many different meanings it has, it's just identified by that one string. So I have the modal auxiliary and the can of beer, the flies is all in the one vector. And when people came up with this, many people worried, like in linguistics, you can't do that, it's terrible and stuff like this. But it turns out that these embeddings are so rich that depending on the context, when you contextualize this, the rest of the context always kind of like uses the right bits. So if it's a modal auxiliary, it will take the modal auxiliary part, in these numbers, simplifying a little bit. But we get there. This was a really good question. Okay, and so and something like this was also, yeah, you have. Mm-hmm.
So these vectors would be relational or absolute? So the word is described with the connections it might have, or is it on its own?
So the question is, how do we compute those? How do we get them? And we get them by kind of like looking at an intuition that comes from linguistics. And that's the distributional hypothesis by two people, Firth and Harris. Some of you may have come across that. And what they said, kind of like, that was sort of like the old British kind of like, very like scientific and stuff like this. And they said like, what's meaning? How can we describe meaning? It's like, we can only use words to describe meaning. And then it's circular and everything like this. So they came up with this idea, and it was coined into the slogan. I can't remember whether the slogan is from Firth or from Harris. To know the meaning of a word, look at the company it keeps. And to first approximation, words that occur in similar contexts tend to have similar meanings. So if you look at couch, sofa, settee, they probably occur in documents or sentences that talk about your living room. IKEA, some new, I don't know, style of interior design or something like this. And contrast that with algebra and zebra. So the kind of texts where you find the word algebra are probably the kind of context, I mean here, the words around it, are probably very, very different from the kind of words you find around sentences or documents with zebras in them. Yeah, that's kind of like the idea. And that's what is used in this vectorization. I mean, the people that did the vectorization, they didn't know about Firth and Harris. But actually, what they did, like in library science and early information retrieval, early information extraction, then chimed very strongly with these intuitions by the British linguists, who did this, tried to do this manually. Okay, so ideally, what we would like to have is a representation of words as vectors. And let's say here is a three-dimensional space, because anything else other than 3 dimensions, kind of like it's hard to visualize. Kind of like the examples that you saw were 100 dimensions already. But what we would like to have is a representation of words as vectors where cherry and strawberry are pretty close together because they're fruits. And then we have sumo, basketball, and football. They're sports, so they should be closer to each other, but a little bit further away from the cherry and the strawberry. And maybe kind of like basketball and football is kind of like a bit closer to each other because it actually involves a ball you can kick. And sumo is like, burly fellas trying to push each other out of a circle. Yeah, it's a sport, but it's like, yeah, so that's what we would like to do. So how can we get this? Okay. So here's how people in information extraction, information retrieval did this from count-based word text, where the actual words are represented as themselves. They're just they're strings of characters, okay? And they did this in a data-driven way. So here we have 4 documents. I don't know whether you can read it from where you sit. So the first one is like, we like to play some sport in the afternoon. I like basketball, but John likes sumo more. Okay, it's the first document. It's just a sentence, sentence 1. The second one is sumo is a sport where a rikishi attempts to force another wrestler out of a circular ring. Yeah? Maybe from the Wikipedia or something like that. Fourth one is about Messi, Lionel Messi. Messi scored 4 goals yesterday and kept the ball as a memory of this fantastic sports afternoon. And the fourth document, a single sentence again here, is I ate too many cherries yesterday. Okay. And the first thing that these people in information extraction, information retrieval, but before them also already library science did, is kind of like, they said, if you look at the words, they look very different to me. Some of them are just function words. Okay, so like all the ands, the ors, the conjunctions, the coordinating conjunctions, the pronouns, the prepositions and stuff like that. So we're just going to do away with it. Like, the engineers talking, yeah, because they were like, that's what they were. So they end up with a vocabulary of just the content words. People also call this open class words because the closed class is the function words. Closed class words don't change over time very much. I mean, it takes usually a generation or two to invent a new preposition, or coordinating conjunction happens as well, but it's much more stable. And the open class words are usually the nouns, the verbs, the adjectives, the adverbs, and stuff like that. They change all the time, kind of like, because old words are dropped from the language, new words come in because we change our environment changes. So languages are actually hyperdynamic in that sense. But so they just pick out all the function words, kind of like. So they're left with that vocabulary, like play, sport, afternoon. You see that? It's just the content words that you find in those 4 documents. And then what they do is they do the following. They construct a matrix. you have seen matrices before today, but here it's actually a matrix, and it's called a document term or term document matrix, where what you do is, like in the x-axis on top, you just list all the vocabulary that you found in those 4 documents, okay? And then in the y-axis, you just list the documents, the first one, the second one, the third one, and the fourth one, okay? And then what you do is, you put a 1 under each word and document where you actually find that word in the document, okay? And everywhere else, 0. Yeah. So, for example, the word "like" you find twice in the first document, but you don't find it anywhere in the second. Yeah. And and sort of like some refined versions of this, they actually record also the number of times you find this in the document, and that's what they've done here. Okay. And this is then called a word term occurrence, co-occurrence matrix. Yeah. Everybody with me? Yeah. And if you look at this, now we have vectors already. And what do we have vectors for, if you look at this? By just kind of like, lining this up, kind of like, taking all the vocabulary, maybe ordering the vocabulary in some order, maybe alphabetical or so, but doesn't matter as long as you keep that order, okay? Where can you see vectors? Okay, here's a document vector. That vector describes document 4 in terms of the words that are in it. And it's different, it's a different vector compared to document 1. You see that? Really, really different. But now look at these fellas here. These are word vectors, okay, already. Yeah. Okay, so here you've got a vector for basketball, a vector for sumo, and a vector for cherry. And if you look, the basketball and the sumo vectors, they agree in the first dimension because they co-occurred next to each other in document 1. Okay? And that's really different to the vector for cherry. If you look at the basketball and sumo, kind of like, none of the ones in cherry overlaps with any of the dimensions of the ones for sumo and what is the other one? Basketball. You see that? And you see that geometrically, by just doing that, actually sumo and basketball are closer together than, yeah, in that space. If I just use, like, I don't know, a cosine similarity or, I don't know, some other geometric similarity, yeah? And it comes from the fact that words that have similar meanings tend to co-occur in similar contexts. Because here, like the cherry or the other fruit didn't occur in the sumo. Yeah, and did you get it? Okay, right, very good. And so now kind of like, so you have a mapping already of the words here now in 4-dimensional space and the documents in, I don't know, what is that, 15-dimensional space or something like this, where the similarity of meaning between words has been translated into proximity in the geometric space. Yeah, so you get something like that. And you can actually compute the similarity between these words, the vector representations of these words, in terms of simple geometry. You can use Euclidean distance or cosine distance. Yeah. So cosine distance is about the angles between the vectors, because like, if I go back here, kind of like, the vector for cherry would go from here to there. The vector for strawberry would go from here to there. And the angle between them is pretty close. Okay. So high cosine similarity, The Euclidean distance is the distance between the end of this vector and that vector here, kind of like, pretty close. And here, if you go from here to there, Euclidean distance is pretty far away. Yeah. You get the drift. Yeah. And that's how early information retrieval, information extraction, a sophisticated version of that is TF-IDF, term frequency, inverse document frequency, with a little bit of maths around, or BM25s. This is how old Google worked, donkeys years ago. And even libraries, your colleagues in library science, they would be sitting here and just yawning. Josef, what are you telling us? Of course, words are vectors. No, nothing else. Yeah, but to us, was strange. Okay, so that's the first. But this works on what is called count-based approaches, where I'm just counting the words, and each word is just represented by itself. Yeah, you get that? Yeah. Okay, great. But nowadays, what we do is, we don't do this count-based stuff, but we learn these word embeddings using simple neural networks and just using massive amounts of text. And here's one way of doing that, and it's called word embeddings, and it goes back to work by Tomasz Mikolov. Okay, and the idea is the following. The idea is that the thing you have on the left here, let me just go there, that this is kind of like a little neural network. That's kind of like a neural little network. Okay, and here you run this neural network over text that you find on the internet. You download Wikipedia, for example, all of Wikipedia. Okay, and this is the word you're trying to predict. It's in the middle. And you see the two previous one in the running text, and you see the two words before it. Previous ones and the two words after it. And you pretend that you don't see the one in the middle, and you're trying to predict that word here from the two previous ones and the two following ones. Yeah. And of course, in the data, I have all the information. In the data, if I have this window of 5 words, I always know exactly which two previous words there are, which two words after they are. And I also know the one in the middle, but I pretend that I don't know it. So I try to learn that these words are predicting this one here at the level of neural networks. So these are neural networks. And I can compute an error. I can, initially all the weights are randomly initialized. So these are more complicated neural networks. I just drew them as boxes, but they're trying to predict that fella here. So for example, here, let's say the piece of text was syllogisms are inference rules capturing logical blah, blah, blah. Or something like this, I pretend that inference, I don't know. I have those two. I have neural representations of those, initially completely randomly initialized. Okay. I try to predict a neural representation of that fella over here. Initially totally, bonkers, because everything is completely random. But I can compute an error because I know what I should have predicted, because it's in the data. I can look it up. Okay. And I can use that error to backprop through this, and over time, kind of like I move these 5-word window through gazillions of text, and that way it will learn over time good representations that look like, these 100. Do you remember that picture, the time flies picture with 100 numbers? And I only have to predefine the dimensionality, and usually it's 128, 256, 512, the powers of 2. Kind of like depending on how rich how much data I have and stuff like that. And there's an alternative version. So here, kind of like I pretend that I don't see the one in the middle, kind of like. And the other versions, this is the continuous bag of words, kind of like, because I actually take the representations of those two words and merge them together into one big fella. And then from that fella, I predict the one that is supposedly missing. Okay, that's why it's called continuous bag of words. And I don't even look at whether they're before or after. Kind of like the model loses it. It doesn't care about this. And this one is kind of like a system model that just goes the other way around. So I have the one in the middle, the word in the middle, inference. And the task is to predict syllogisms are rules capturing, the two before, the two after. But otherwise, same idea. Randomly initialized. I know which ones I'm supposed to be predicting here. Kind of like, so I can compute an error. Yeah. There's actually more to this, like, to to actually scale this to hundreds of millions of words and stuff like that, you have to do something else but that's in the papers. But that's the basic idea. Yeah. So this is completely prediction based. So this was, So this was count based. Yeah, where the words are used as discrete units. And if I want to do this for big data, I might have like, I don't know, 100,000 documents and vocabulary of 50,000 words and stuff like that. But you can do that. Yeah. And this here is prediction based, where I'm using machine learning, simple neural networks, actually classification, but kind of like to learn these embeddings, kind of like, and what I do is kind of like, I do something like this. So here I've my text data, like, she ate the soup with a slice of bread. It's the first sentence of like, I don't know, let's say a corpus that has 100 million sentences or so in English. And then I just move those 5 word windows across. And either I'm predicting the one in the middle from the knowledge of the 2 before and after, okay, or the other way around. Yeah. Okay, and this is called now, and that's important, it's self-supervised learning. Before, we're talking about supervised learning, where we as people had to manually label the pictures with doggies and cats. Here, the data brings its own supervision signal because the word in the middle is there. I'm just pretending it's not there and I have to learn it. Yeah? Okay. So this can be scaled to umpteen gazillions of data. And that way, these embeddings will learn a bit about grammar, about meaning, about domains and stuff like that, fully automatically, without being told. There's nothing that tells them kind of like, some of the stuff that I show you. Now, and you see the SOS and EOS there? Kind of the SOS is just, the engineers, they smuggle in start of sentence invisible symbols to have the first 2 words on the left. So that's how you can learn, like, whether a word that you find, is often at the beginning of a sentence or, stuff like that. And same for end of sentence. You smuggle in these 2 invisible kind of like, they're just added. Yeah, but there's no magic about this. Okay, so that's self-supervised learning because the data that you have already carries the supervisions. Okay, and that's what makes it possible to scale some of these stuff. For the other approach, you have to have humans to label 100,000 cat and doggy pictures. Yeah, here, no, you just download all the Wikipedia or like, half the internet if you have the money. Okay, and then if you do this, okay, and you plot these word embeddings, kind of like, and here's a 2-dimensional projection of these, like, I don't know, 512 dimensions, you see amazing stuff happening. You see that kind of like, so here's a space in the 2-dimensional projection where city names occur. Here about feeling, like depressed, happy, elated, and stuff like this. This may be like kinship terms, mom, dad, blah, blah, food, body parts, and it's just a tiny, and you can really see that that similarity in meaning to first approximation goes into proximity in the space. Yeah? And that the closer they are in space, the more similar they are, by and large. And so we have a graded notion of semantic similarity, completely computed from surface, but where we have this proviso, we just plunk together everything. Every time we see can, doesn't matter whether it's modal auxiliary or is a noun, it's together in the same vector. Yeah, at the moment. Okay. And then if you look into the space, okay, so this is now taking the magnifying glass, and you look into the space, and these are again sort of like 2D, what you call it, 2D projections of this, like, I don't know, 500 dimensions or 1,000 dimensions or something like this. And then you can see that if you look at some of the terms, kind of like, they're related in terms of being shifted the same way. So look at this one, man, woman, uncle, aunt, king, queen. What's the relationship between them, if you're a linguist? What's the relationship between man, woman, uncle, aunt, king, queen? Gender, yeah, plus, minus, male, female, okay? And you can see that these semantic features in that space are represented by similar shifts, okay? And that suggests that you could take the embedding for men, kind of like, and somehow shift it to woman, because that's just a vector, if you like, yeah? You see that? Yeah, and it's not just meaning, kind of like, so here, for example, it would be like, I don't know, what is that semantics called? Componential semantics that linguists try to do manually. You know, plus minus male, female, plus minus alive, or I don't know, stuff like that. Nothing that told the system to do that. It's what you get in the space from this idea that words that are similar in meaning tend to co-occur in similar contexts. Look at the other one, king, kings, queen, queens. So king and queen, that seems to be, again, that plus minus male thing, you know, that shift in the space. What about king and kings and queen and queens? What's happening there? Yeah, number, morphology, okay? So you've got meaning, you've got morphology, you have some domains and stuff, which you just learn from this like co-occurrence prediction. You get similar things with if you do the count-based things, and there are papers about kind of like, you know, why the prediction base may be better and stuff like that. But I don't, you know, not nowadays we just do this completely by prediction. Okay, and now what you can do is you can compute with words, and by compute I mean like subtraction and addition. Okay, which kind of like is an absolute dream that, you know, that people never thought, you know, well, we can't add two words, we can't subtract a word from another one. No, you can. So if you take the vector for king, okay, and from that vector, you subtract the vector for man. And by subtraction, I mean element-wise, by dimension subtraction, get a new vector where each of these guys is the difference between those two. So you have a new vector there. And then to that, you add the vector for woman. And by adding, I mean element-wise addition, new vector, same dimensionality. You get a new vector. And if you take that new vector, you go into the vector space, into that point, and you look at what's the next vector, actual real vector from the data that was computed in there. It's queen. Okay, and that's also how you evaluate these systems that do this completely automatically. So you've got like ranges of such computations where you let humans predict what's the closest, and then the evaluation of these embedding systems is usually like, you know, how many of the top 1 agree, of the top 2, top 5, and stuff like that. Yeah. Okay, here's another one. So this is now analogical reasoning in vector space, not just vector subtraction. And you know, analogical reasoning is A is to B, what C is to D, or something like this, you know, and then you can move the stuff. So if you look at this one here, Madrid is to Spain is the same as Rome is to Italy. What's the relationship between them? Usually it's about relational information. What's the relationship between Madrid and Spain and Rome and Italy? It's capital, yeah, it's capital, yeah? Okay, now do the following. Take the vector for Madrid, subtract everything that's Spanish from the vector of Madrid. That is, take the vector of Spain that you computed automatically in that vector Spain, and add the vector of Italy to that. What you get? Yeah, you get Rome. Yeah. So you take Madrid, you take out everything that's Spanish in that vector. So you've got sort of like, you know, some kind of like abstract is capital of, and then you infuse it with everything that is Italian. Kind of like, you know, what about Paris minus France plus England? What do you think? Yeah. What about sushi minus Japan plus Germany? Yeah. Yep. Yeah. And these are computed from data. It's just like, you know, you just plonk the words in there, you do the word embeddings, you do this for 100 million. Okay. Kind of like, you know, and notice the equality here. The equality is not an exact equality because it's a new vector that's somewhere in the vector space. And you generally look around what's the closest vector. And it's not always the closest, but it might be top 2, top 3, or something like that. So for example, beer is also very close second for bratwurst, for example. And you can see that these systems learn, what was that? What we called in linguistics, differential meaning, plus minus female and stuff like that, this stuff. They can do this. They learn singular plural. So like, you know, grammatical information. They learn cultural information. This is not grammatical at all. You know, it's factual information about capitals, and it's like, you know, I don't know, bratwurst or beer or, yeah, okay. And really just from, okay. And so these word embeddings are not just kind of like cool for getting us into neural networks, but we can do something with them. And pretty much all NLP that's happening for the last 10, 15 years, 15 years close now, uses word embeddings in some sense or form. These are also called latent representations because they are vectors, kind of like, you know, in dense vector space. And you've got this super nice thing again, which I wanted to point out, that the closer words are in meaning, the closer they tend to be in the vector space. So you have actually a geometric notion of similarity in meaning that is totally graded, 0.5, 0.38, -2, or stuff like that. Okay, yeah. Yep. No, only once. So here you just brutally conflate all the meanings. And you can tease this apart. And one way of teasing this apart is, for example, using part of speech tagging. So here some linguistics comes in, because sometimes, for example, with can is a modal auxiliary, is a different grammatical function to the noun can or beer. And a good part of speech tagger will get the difference. And then you have can noun and you have can modal auxiliary, and you have two different symbols, and you have two entries. And as I said, like, people worried about that a lot, like 10 years ago, 15 years ago when this came out, because they say, oh, can't do that, it's terrible. But then it shows if you use this in machine translation, if you combine this, that's usually just the input in the neural network. The rest of the neural network, given a particular context, will just single out part of the embedding that is relevant. And because what we're going to do, these are called, it's a very, very good question. I should have put that on the slides. These are called static word embeddings, because they're not contextualized. This is just for the whole data. I've got this one embedding, and that includes information for can as modal auxiliary, for can as, yeah. And exactly, the intuition was that this, is doomed to failure. It can't work, Does, yeah. Mm-hmm. Hi. Mm-hmm. Yeah, 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 very good question. Okay, because so all of these words are initially associated with a vector. Yeah. And this vector I randomly initialize. So I've got a huge matrix, kind of like, and the matrix is the dimensionality of the vector, like let's say 512 dimensions for each, and the size of the vocabulary. Okay, let's say I have 50,000 words in the vocabulary. I've got a big matrix, okay? And I have a mapping between the 50,000 and the 50,000 words in the vocabulary. This is called a hot one encoding. So initially, each word is encoded with a 50,000 vector that has only one one in there. Everything else is zero. And I just do that according to where the word is in the position in the alphabet, some ordering, okay? And I order the random vectors the same way in the matrix. And then for each word, I take its hot one encoding multiplied with the matrix, and then I get just that random vector for that word, okay? And these big matrices are then like, how the vectors in these big matrices are then how the words are represented inside the neural network. And they're initially just random. And so initially the weights are all random. So initially the prediction of the missing word in the middle will be completely bonkers, okay? But I know what its representation should be like because I have the word in the middle. And then I can compute an error, back propagate them through the neural network. I do this for like, I don't know, 100 million sentences, and then after I do that, I have these fellas. And these fellas then have these properties. Yeah. But something like this you can also already see with the count-based ones, where I do the term document matrix or the word. There's also a version of this where you do this word based. And you can use principal component analysis also to make them dense and stuff like that. So if you may have come across that, especially if you're in linguistics, is an alternative way. But this one is how it's done nowadays, and it really truly scales. And yeah, okay, all right, okay. Oh, yeah, sorry. Yeah, very good. So like most of the examples that are shown here are cherry picked. Yeah, but the systems are evaluated against human associations, and the evaluations are then kind of like, is the automatic prediction rank 1, rank 2, rank 5, or something like that, and you can then look at the systems. Yeah. 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 There's human evaluation through the data sets that you evaluate against. Yeah. The names for these data sets, I can't remember the names. You need this for different languages and stuff like that. It depends on the training data that you have and how good they are. Yeah, but of course, kind of like in the papers, kind of like, they usually give like some that are funny or like nice, but they give also, they give you the full evaluations, and you see that in the rank 1, rank 2, rank 5. Yeah. Okay. And okay, so that was all I wanted to say at this stage about neural networks. And now we come to the second ingredient for large language models, and that is language models. Okay. And what I want to do is, initially, I want to go through language models the old way we used to do them. And this is count-based discrete language models. And what count-based means is that we have the words. Each word is treated as an atomic unit, and that has sort of like, as a string of characters, and that has strong consequences on identity, for example. So under that strict view, where we look at words as discrete and count-based, the only similarity between words is identity. Because if you change a word by one letter, it's a different word, kind of like, Okay, and what you've seen in the word embeddings, you've got this really nice graded notion, this proximity in vector space and stuff like that. But initially, I'm going to explain the language models like the old way, just to get the intuitions right, what they do, what they're for, and stuff like that. And then we're going to combine the neural stuff with the language models and get the large language models. Okay, so language models, so the basics. So this is where, I should have swapped you, kind of like, because you guys have the crick that way, and these guys have the crick that way. So like, so you have to expect major damage tonight. All right. Okay. So what we're going to do is now is like, this is the part where we have even more audience participation than in other bits. So I really need you now. Okay. So this is about English. And I don't know, is anybody here whose first language is English? Me neither, by the way. I don't know why I raised. Okay. So nobody, but I think this is going to work anyways. It's I would like you to suggest a likely next word, given that the context that you've seen is once upon. Only one. Who's for a? Very good. So let's check. Aha. Next word. So now I have a context once upon a. Next one. Aha. Very good. Next one. Now I have a new context. Once upon a time. Yeah, so people are kind of like, it's all possibilities. Yeah, some are maybe more likely, some are a little bit less likely. Next one. Now I have 1, 2, 3, 4, 5 context. Yeah, okay, so you get the hang, right? That's one thing a language model does. Kind of like, given a context, it tries to predict likely next words. And of course, it's not unique. You have choices and stuff like that. You have some things that are more likely, some things. And what you just saw is that part of what you have as part of your cognitive activity and your language facility is a language model. Okay. And so large language models kind of like some of the stuff that you have, Okay. More examples. Okay. The clouds are in the, sorry? Sky. Okay. So it's kind of like factual information. Yeah. Yesterday I went on a shopping. Yeah. That's kind of like, yeah. What do people call that? A collocation or something like that in linguistics? I think it's a strong kind of a 2-3 word phrase, something like that in English. But you could also say bonanza, extravaganza. A disaster. I went on a shopping disaster with my yeah. So but there are also words that are very unlikely. If I say yesterday I went on a shopping under or and somehow maybe possible, but not very likely. Yeah, you see that? Yeah. So what a language model does is it tries to predict, given a context, at that point, a probability distribution over all the words in the language, all the 50,000 or 100,000 or 500,000 or something like this, how likely they are in that particular context. Or not. Some are more likely, some are less likely, some, yeah. Napoleon was the emperor of, okay. I lived in France for many, many years. I speak almost perfect. Yeah. And you could see that this context could get very large. I could say, I lived in France for many, many years. I love the food. I like the wine. I still have many, many friends there. I like to go back twice every year. Unfortunately, I still don't speak good And you see that, I love France is like, miles away. Yeah. So these are in linguistics, they are called non-local dependencies, and every language has that. Kind of like, so these kinds of, but also grammatical ones where you have like separate prefix verbs, where you have the verb and then the prefix comes like, I don't know, 12 pages later in the sentence, and it completely changes the meaning because the prefix is, anmelden, abmelden, and stuff like that. You get it in every language, so all human languages are like that. It's not a design flaw or anything like that. Far from it. It's actually one of the reasons why they are so efficient and so amazing. Okay, so you can do this. We clearly have language models in our heads, which are part of our language facility, maybe our intelligence or something like that. I don't know. We'll see. Okay, and here are some likely examples. But what's happening here is essentially a prediction. Okay, a prediction where we use the past in order to predict possible futures according to different likelihoods, probabilities. Yeah, because we could say other things there, but maybe the most likely ones. And I think you were pretty much in agreement about maybe the most likely ones. Okay, so how do we do this? Kind of like, so in language and elsewhere, past can be used to predict the future, and that is one thing that language models do. Okay. And what is more, you've just seen it very, very clearly, and you would see that even more clearly for your native languages, that each one of you has a language model in their head. They're not exactly the same, but they agree on many things. Depends on what you've read, your upbringing, and all that kind of stuff, kind of like, Okay, so how do we model this? So what is modeled here? I just want to make that once. It's not just the next most likely word, but it's a probability distribution. The blue thing is the context. And the red thing in that slot is all possibilities. That's the complete vocabulary in all the language. And a language model tells you something about each one of these probabilities or possibilities, even the most unlikely ones. Yeah, that's what it's supposed to do. Yeah. So some of these are like shopping spree, very likely. Bonanza, a bit less likely. Extravaganza, disaster. But event on a shopping, never. On a shopping, other, probably very unlikely. Very. And if you want to model this, how could you model this using probabilities? What trick do we use in probabilities if we want to model predictions from the past on the future? Yeah, yeah, we're counting in count-based models exactly to estimate these probabilities. And what are these probabilities? There's a special type of probabilities. Yeah, yeah, and statistical. Yeah, it's conditional probabilities. Do you remember that? We have probabilities, just general probabilities, and we have conditional probabilities. So conditional probabilities is given that something happened. Yeah. So for example, given that I have a six-sided die that has the numbers 1, 2, 3, 4, 5, and 6. And I cast that die. What's the probability of, I don't know, getting the number 2? It's 1 in 6 if the die is fair. What if I know in the conditioning part of the probability that I cast a die and I disclose to you the information that the number I got is is even, not evil. What's the probability of 2? Given that the number I got is even. 1 in 3, very good. So you can see that information about the past can change the probabilities, yeah? So conditional probabilities, and that's what we're using here. We're using, using statistics and conditional probabilities to model these language models. So, but before we get there, language model can predict new words, can compute probabilities for next words, can compute probabilities for entire sentences, because I know the probability of each word, and then I can put them together in a clever way. Probably something to do with multiplication that gives me the probability of the whole sentence. Can also generate text. Do you remember when we did this example once upon, I used your prediction, extended the context, then you made the next prediction, so you generate a text. That's what a large language model does. A large language model has a prompt which defines the context, and then it generates from what it has learned given the context of that prompt. Okay? So you see the large language model is looming. But at the moment, we're doing everything count-based. All right. So how do we model this? Like predict the next word, it's conditional probability. So this means kind of like, what's the conditional probability of the next word, that's the red one, to be spree, given that the context, I went on a shopping. Yeah. And if you put this in symbols, kind of like you say, what's the probability of word J given that I've seen everything from word 1 in that sentence all the way up to the previous word, to j. Word 1 to j minus 1. You see that? That's all it says. Everybody with me? Yeah? Okay, so that, that can be used if I have these probabilities. I can compute the probability of next word given context, and I can also compute the probabilities of a sentence. So for example, given that I want to compute the probability of how's it going, question mark, okay, like where in that sentence I have 1, 2, 3, 4, 5 tokens, words, like how, is, a separate token, it, going, question mark. Question mark is also a word, it's a token, kind of like, okay. Then I can unpack that. I can say kind of like it's the probability of saying how times the probability of, given that I've said how, or the probability of apostrophe s, times the probability, given that I said how's of it, times the probability of going, given that at that stage I've said how's it, times the probability of question mark, given that I've said how is it going. You see that? Yeah? And that's an exact mathematical equality. That's the chain rule of probabilities. Yeah? Okay, so if I can compute those guys, I can, if I have a way of not computing, estimating, because we're estimating these probabilities from data. That's how statistics works, text data. If I have these, I can, given a context, I can say something about probability of next word, completion, kind of like, extending the thing. I can say something about the probability of entire sentences, if I have all these individual probabilities. And I can also generate text. I can give a context and then tell the model, yeah, please kind of like, give me a likely continuation as next word, where it samples over that probability distribution. It more likely picks likely words and it less likely picks less likely words according to these probabilities, but it's a random process. But it more likely, and then, extend that text by that word and then pick the next word so it can actually generate. Yeah, okay. Right. So yeah, it's just in the whole thing. Once again, in mathematics, we're just in symbols where we have W for word and numbers and stuff like that. But it's the same that you found on the previous page. So how can we estimate them? Kind of like, estimate those probabilities. We always estimate them from large data, and the more data we have, we hope that the more accurately these probabilities reflect the true probabilities in the language. We never know what that is. But if we kind of like, this is the old example in statistics. If there's an election, okay, and let's say election in here in Slovenia, if you asked prior to the election every voter, and every voter was truthful, kind of like, you knew the outcome, okay? But of course you can't do that. You only see a sample, like, I don't know, 5,000 people or something like that. And then, yeah, and the same here. We never have all the text that humans produce, say, and stuff like that. But we take a large data set, we get probability estimates from that, and then, the more data we have, the closer they are to, we think, to the real thing. That's the game here, kind of like in statistics, yeah? Okay, so we're going to do these count-based discrete language models later on, the neural language models. And let me just skip over this one. Okay. And yeah, so how do we do this? And I'm not quite sure. I think I forgot to include a slide here. So let me just try to explain this. So our sentence here is the top line in blue. A sentence is like, n words. First one, second one, all the way up to n, okay? So of course we could use the chain rule of probabilities. We can say that the probability of that sentence, where that sentence is these n words, is the probability of the first word times the probability of the second given the first, times the probability of the third given the first two, all the way up to times the probability of the last word given all the previous ones. Yeah? Okay. And we estimate each one of these probabilities. So this, let me go here. So this probability is a unigram probability because there's no context. That's called what's called unigram. That fella here is called a bigram probability because here's the context of the previous word. This fella here is called a trigram probability because the context is the two previous words. This would be an n-gram probability because I predict the word given the n-1 previous one. So that's always context. So what's after the conditioning part is always the context I have. Okay. Now I can estimate them, these unigram, bigram, 3-gram, 4-gram, 5-gram probabilities by just looking at lots of text data. So for the unigram probabilities, I just count for what's the probability of the word like hello, I download the Wikipedia and I don't know, the book corpus of all the novels in English of the last, I don't know, 400 years or something like that, then I count how many times do I find in that book corpus the word hello, okay? And I divide it by all the words in the corpus. Yeah, that's an estimation of the probability. It's kind of like the idea is that you close your eyes, you randomly open the book, you put your finger and then you open your eyes on the page, you know, and what's the chance that your finger is on the word hello? That would be that probability. Yeah, everybody with me? Okay. For the bigram probability, we have context. And the bigram probability, we just estimate by counting how many times do we see, like, you know, hi there, for example, hi followed by there, you know, and we divide it by the probability of hi. Yeah, because this tells us how many of the occurrences of hi are continued by hi there. You know, another way of saying this is how many times of finding hi in any other word following hi, how many of these following words are hi are there? Does everybody get that? Yeah, it's kind of like trivial, but let me just belabor this. And we can do this for the higher n-grams as well, for the trigrams, for the 4-grams, and stuff like that. Can anybody see a problem with that? Yeah. Yeah, exactly. Because the longer these contexts are, no matter how big your text, you're not going to find these contexts. Yeah? If you think about, let's say we have, we take a large English dictionary, yeah, one of the really large ones, you know, the Webster heavyweight, kind of like, you know, with 500,000 English words or something like this. Then you have, in theory, you have 500,000 one-word English sentences. How many two-word English sentences in theory do you have? Yeah, 500,000 times 500,000. That's already a lot. How many three-word in theory? They're not all grammatical and stuff like that. 500,000 times 500 times 500. You see, so it goes exponential. And yeah, no chance, kind of like, you know. So for the longer n-grams, kind of like, you know, you can't estimate them from data, no matter how big they are. And because of that, in these count-based systems, you do something. I mean, there are clever things like smoothing, back off, and stuff like this. But there's too much here for the class. But you do something that's called the Markov hypothesis. And the Markov hypothesis says, like, you know, okay, we're just approximating. We're not looking at these longer n-grams because we can't find them in the data, but we pretend that the languages that we speak are only determined by the first word the last word that we see, or the last two words that we see, or the last three words. So you just limit the n-grams, you know, you don't go further into the history. And that's the Markov assumption. Okay, yep. Okay, that's the problem here. I think the problem is that we don't find these longer n-grams in the data. So we use the Markov approximation, and the Markov approximation only looks at, I don't know, bigrams or 3-grams. Here's an example, for example. Here's like the sentence, how is it going, that you saw earlier on. And here we're approximating that by a bigram Markov model, where the model says, you know, we're only looking as the context at the immediately previous word. You know, that's not true. I mean, you saw that. You remember, like, you know, I used to live in France. I still go back twice every year. I love my friends there. I really like the food. And boy, can they party. Unfortunately, I still don't speak. Yeah, so you can clearly see that's a massive simplification. But it's like, you know, okay, so that's a bigram Markov approximation. This is a trigram, kind of like where I say, kind of like I use and I can estimate them. You know, then for them, I get pretty good data. Okay. Okay. But it's not sufficient. And here you see an example, like the French example was an example like this. If you look at this string here, I hire men who is good pilots. What's wrong with that sentence? The number, yeah. So the is does not agree in number with men. Men is plural, and the main verb of the relative clause is the wrong number. And if you used a bigram model, it would give you a very high probability for the sentence because it doesn't see the mistake. Because it says that's the probability of who given men times the probability of is given who times the probability of good given is. Okay? And this is fine. Kind of like if I say who is the context and then is quite likely. It doesn't make the connection. Yeah? And a trigram model would. It would give you enough context, give you a very low probability. So if you have enough data, a higher n-gram model is usually better in count-based language modeling. But at some stage, you will inevitably run into this problem that for the longer n-grams, you cannot estimate them. So you have to do lots of maths. And this is a limitation. But usually, like the highest count-based language models for English that we used before, like neural networks, were 5 gram, 7 gram. 7 gram was really like, you know, the Nice bees, or 10, 15 years ago, were He-field models from Edinburgh. Okay, and here's just a fun thing, kind of like, you know, here's we've trained, or not we, this is from a textbook. We've trained unigram, bigram, trigram, and quadrigram, 4-gram models on Shakespeare and used them for generation. So let me share the art here a little bit. So the unigram model. To him, swallowed, confess here both, which of safe on trail for our a device and road life have. Yeah, it's very artistic. Okay, bigram model. So now every word is conditioned on the previous word. What means, sir? I confess she, then all sorts. He's trim captain. Okay, some better, yeah? Trigram model. Sweet prince, Falstaff shall die. So trigram conditions on the two previous words, you know? Sweet prince, Falstaff shall die. Harry of Monmouth's grave. You know, quadrigram. King Henry, what? I will go seek that traitor Gloucester. And then really cool stage directions. Exeunt some of the watch. So, and how the watch is walking off stage. And then what goes, a great banquet served in. Yeah, cool. You see the power of these. This is just training these probabilities, or I should say estimating, not training. Yeah, estimating these probabilities from just Shakespeare. Yeah, and a 4-gram model is already kind of like, you know, and here the model is used in generation. So you give it like, you know, the first 2 words or something like this, you know, and then you say, no, and a unigram model will just take like, you know, will draw from the probability distribution over unigrams in the language. It will just pick something that's pretty likely, you know, and more likely the more likely ones, less likely the less likely ones, and then new context, next word. A bigram model will just condition on the previous word, and it becomes more Shakespearean. And, you know, trigram model and 4-gram model already, yeah, do you see, kind of like, you know, and large language models do this, but with a context of like thousands of words. Oh, I don't know. I mean, here maybe just the first word, or maybe the first 2 words in the bigram, the first 3 words in the trigram, and the first, or probably some context. The context is appropriate to the model. This is from, I don't have the quote here. This is from the, you see, like natural language processing is so fast in many parts of machine learning, and that there are no printed textbooks anymore, because by the time the textbook is printed, you're out of, kind of like, it's too old. And that's why the textbooks that do exist are only on the web, and they're updated all the time. And it's from one of them. It's for the guys from Stanford, and maybe some of you have seen this before. The name's probably going to come back. Yeah. But it's really cool, isn't it? But you can see that just a few words, context, you know, and already becomes, yeah. And the only thing that this fella has done is counted words and divided them, kind of like for conditional probabilities, nothing else. Yeah. And yeah. Okay, and now we're getting closer to putting it all together. So you've seen neural networks, you've seen count-based discrete language models, where we've got that problem that, you know, like, given the amount of training data that we have, we can't really model a lot of these interesting longer histories because we never see them. Okay, and if we never see something in statistics, its probability is estimated as 0. Yeah, and you see, you compute these probabilities in a sentence. I just multiply all the probabilities, and if there's one n-gram in there that I don't see, there's a 0 in the multiplication, and everything goes 0. Yeah. Okay. All right. And what we're now going to do is we're going to go and put the neural networks and the language models together. Okay. So the count-based discrete language models are cool. They're also kind of like self-supervised because all the data is in the data. Yeah. I can count. For the unigram probabilities, I just look at what words do I have in the language. Okay. And then for each one of them, I look at, you know, the first word in the dictionary, like about or something like this. How many times do I find it in the data? And I divide it by like all the numbers of the tokens of the words in the data. And that's the unigram probability for about, you know. And for the context, I just, you know, have these two terms and I divide them by each other. Yeah. All right. So, but the context is limited, you know, because of no matter how much data, no chance. We won't ever see everything, but the neural networks now come to the rescue. Okay, and just reminding yourself of these word embeddings, kind of like, you know, time flies. That was already a language model. It was a language model where the context is the two previous words and the following. Okay, it's not just a complete prefix, but it's a language model that has a context left and right. Do you remember that? Where I predict the word in the middle, or whether I'm given the word in the middle and I'm trying to predict the two before, the two after. Yeah, these are all already language models. It's just not kind of like they're conditional language models. They're given context, but they have left and right context, not just left context. Yeah, the one that has only left context, the one that you've seen like with Shakespeare, the fancy term for them is autoregressive language models. And most large language models, like the neural ones, are also autoregressive. And autoregressive is just a fancy term for predicting left to right. Yeah? Okay. Okay, so this is how we computed these guys, kind of like the word embeddings using neural networks. And yeah. Okay, and here you have some terminology. We have the traditional autoregressive, left to right. But now we want to combine, we want to implement this idea of a language model with neural networks. And the neural networks that we've seen so far are the feed-forward neural networks. Yeah? Do you remember that? We've got input vector, and then we've got these different layers, and we've got some output neurons, like we have the sensing neurons. We can represent them as a vector, the output neurons as a vector. We've got all the stuff in between, and it computes from left to right. Okay, and they're really cool. They're powerful. But once we've defined such a network, it's fixed in the architecture. It has that number of input neurons, 5,000. Okay, and it has that number of output neurons. Okay. But if you think about natural language and the length of sentences, they're very variable. You know, some sentences are only 3 words, like some sentences only 1 word, like hi. You know, some sentence, if you look into Kant, is a little bit longer. And there are others that are even worse than that. You know, they start writing the sentence on Tuesday and finish on Thursday afternoon. There should be a full stop somewhere. So let's do something here. Kind of like, so it's very variable. So what we would like to have is a neural network architecture that can automatically adapt itself to variable length input. Okay, with a feed-forward neural network, we could do it as well. We could just do it, make it very, very big, but then for short sentences, we would just forsake a lot of capacity. Yeah, because let's say this feed-forward neural network could take anything up to 100-word sentences or something like this. Then for the short ones, let's say a sentence that has 3 words, I would have to do 0 computation for another, I don't know, 97 dummy words, because it expects that many things as the input. It's fixed input, fixed output. Okay, so what we want is a neural architecture that can handle variable input, variable output. It just adapts itself to whatever it's supposed to be doing. And that's what we're going to take a look at. So that was a feed-forward neural network, fixed input, fixed output. And this one here now has an example where the number of neurons in the middle is it just varies, kind of like, you know, the ones you've seen before always had the same number of neurons, but, you know, they can have more or less, it can be anything in between. Okay, so it's cool, but fixed input, fixed output, not really totally elegant. So what we'd like to do is kind of look at something else. And the first thing we're going to look at is something that's called recurrent neural network. And one of you asked this question actually in the first part of the course. You know, do we have neural networks that can also feed information back to themselves in a loop? And this is one such fellow that can do that. So this one here, the one on the top right, is a recurrent neural network. And there's other architectures like convolutional neural networks. We're not going to talk about that. They're often used for vision. Here in the lower right, we're also going to look at transformer architectures. So they are important because most of the large neural language models are implemented in terms of transformer networks. There are also things like autoencoders and stuff like that. So there's a whole zoo of neural network architectures. But we're going to look at the recurrent neural networks now. Okay. And let me try to explain this to you. So the recurrent neural network is a neural network architecture that over a number of time steps reads input words, first word, second, third, fourth, or something like this, kind of like, and it automatically unrolls itself to however many words it's fed. So kind of first word, second, third, kind of like. In the rolled up version, it looks like this. Okay, so the input in the rolled up version to the neural network is this fella here. That xi, that is a word. Okay, and the word is being given to this fella here in terms of a word embedding. So that's already a vector. So we have that. We know how to compute them or something like this, yeah? And then it goes into, this is also a neural network. So it takes that word embedding and does some computation with it and produces some output, yeah? Here, this would be the output. It doesn't have to produce any output, but it could. Like one output it could compute, for example, is part of speech tagging. I could train this thing to kind of like, take a word and then associate, is this a noun, is a verb, or something like that, yeah? Okay. In the neural network here, kind of like, I have a hidden representation. Hidden representation is a vector. And that vector is computed from the input, which is this word here, the word embedding for that word, plus the hidden representation, the vector representation of what the network has already seen at that stage. So if this fella is the first word, he hasn't seen anything before because he's the first word, okay? And so this context here is empty. It's just kind of like a vector that has only zeros in there, yeah? And it's combined with that one here to then come up with a new hidden representation of a context that is now consisting of that word where there was no context before, okay? And that way, this fella can unroll, kind of like, because, so the first word comes in, the initial context here, you see this funny shaped thing over there, that was empty, like a context vector with only zeros or something like this. It's combined with that one with some neural network, nonlinearity, there's a sigmoid or something like the usual stuff. I later show a little bit like, what these neural networks look out. And it computes a new hidden representation. And the hidden representation, this one, is now the hidden representation of this recurrent neural network having seen the first word in the empty context. And it might produce some output, part of speech tag or something like this. Then the second word comes. And the second word is like, maybe hi there, The second word is there, the word embedding for there. It's now combined with the information of the previous context. The embedding that records that the system has already seen hi. And it's now combined with a there, computing a new context, a hidden representation in the form of a vector. Kind of like a latent representation that now records the context hi there, and it might produce some output here, The output is again also kind of like a vector, and then I do something with that vector, compute a part of speech or something like that. And then comes the next word. Then the third word is now interpreted in a context representation where the neural network has computed the context of the first two words, where the first didn't have any context, was the beginning of the sentence, and it's integrating the information of the third word from its word representation, word embedding, with that context to produce a new context, which is now this whole thing, kind of like, and maybe computing some output. You get the hang? Yeah? And this can unroll itself all the way up to when it sees the end of sentence symbol. Yeah? And it doesn't mind whether the sentence is 100 words long or 3 words long or 2 words long or something like that. Everybody with me? Yeah? And what this one here, this representation here means is that its internal context representation is delayed by 1 and fed back to itself. So that means the context for this one here feeds into the context for the next word. That context feeds into that one here. Yeah? And that's what this delay here, this fella here says delay by 1. Yeah? So it's not used immediately. So the context defined by this is not used for this, but for the next one that's going to come. Yeah, that's delayed by 1 time step. Everybody with me? Okay. So that's a recurrent neural network. Similar to recursion, kind of like, it's actually recurrence. So this one is called rolled up, this is unrolled, and you unroll it to whatever. And this is very useful for language, because language is kind of like you're always dealing with sequences of different length. You never know how much is going to come. You may also have, if you have input and output, for example, in machine translation, for example, you have input over some length, and the output might be a different length. Might be longer, might be less long, and stuff like that. So you have to map different length input to different length output. And these guys can do that as well. Okay. So here, for example, is like, you see him as a part of speech tagger. So here the sequence is a German sentence. Natürlich hat John Spaß. Naturally John was enjoying himself, or something like this. The first word is an adverbial. The second one is a verb, and so on. Yeah. Here is the same fella as a language model. Okay, because here is trained, like given the first word as context, he's supposed to predict the second. Okay, given the first two, okay, he's supposed to predict the third. Yeah, do you see that? And yeah, and now this is kind of like a hard one. Why do you think is this not subject to the limitation of the count-based language models where the larger n-grams you never see in the training data? Why is this thing happy with something that's never seen in the training data? Any ideas? It's very often, it's hardly ever thought about, but it's important. There's a real difference here. Yeah. Yeah, exactly. That's exactly the reason. Because kind of like it always computes some context, as long as it's seen the word embedding, kind of like, it always computes a hidden representation. A hidden representation is just a fancy name for whatever the embedding there is, the vector. Yeah. And this is just like, updated using error. I have error here in the language model because I know when the prediction is wrong because I can look at the next word. Do you see that? Yeah. And as long as it has seen the word embeddings, it doesn't have to have seen the context because it's always going to compute a hidden representation. Yeah, and it's really fundamental difference. I mean, many people never thought of, but that's the reason. One of the reasons, again, why this stuff can be so powerful. Okay. Yeah, and this is trained by backpropagation. I have an error because I know, like, this is self-supervised for language models. I know what the next word is. It's in the text. Okay. Initially, all the weights are random, and the outputs are nothing like this. God awful. They're all over the place. But for each step, I can compute an error. Okay, and then backprop that error to adjust the weight so that the next time it sees that prefix, its prediction is going to be tiny little bit better. Yeah. Okay. And this is now looking inside. So kind of like, you might wonder, Josef is always saying that this fella here inside is a neural network, but what does that look like? That fella here, that's how it looks like. So that's the previous hidden state as a vector. Let's say here is a vector of dimensionality 4. It comes in there. Like in reality, it's like 512 or 128 or something like that. Here's the current input, word embedding. For the current word the fella is reading. And this would also be like, I don't know, 256, 512, 1024, something like that. Okay. Here are the neurons, and then they are combined into an output that is of the same dimensionality as the previous hidden state. You see it's 4 here, 4 here. And this output is then the new updated state that takes this history, whatever it was, whatever the vector here was, and updates it with the information from that one here. And it learns what to kind of like forget, what's important and stuff, just by backprop. Same idea. And the supervision signal comes from the text because, like, the next word is there in the text. And if you train this on a gazillion amount of data, yeah, everybody with me? Could you formulate in your own words what's the big difference between the count-based and why they have this problem with 3 grams, 4 grams, 5 grams, and why this fella doesn't? Right? Do you see the problem with the count-based ones? That the higher the n-grams, the less likely you'll find it, because like you never see the full variability of these like 500,000 times 500,000 times 500,000, like raised to the power of 10 for a 10 sentence possible example. And you get very rapidly into kind of like that you get into numbers that are more than the number of molecules or atoms in the known universe. It's the complexity of these things, kind of like, And this guy doesn't have to have that, he just computes a prior hidden state, which initially comes from the first word, And then as long as he's seen the word embedding of the next word, he will just compute a new one by that little neural network. And over time, this learns something good. And we're not telling it what to learn, apart from predict the next word. Yeah. Now, these guys here, the recurrent neural networks, the simple ones, they cannot really model infinite context. So kind of like, they're depending on the kind of training data, they try to get they tend to get blurry for histories that are longer than 10, 15 words. They forget things and stuff like that. So similar to us actually. In that but there are versions of recurrent neural network, and they're called LSTM, long short-term memory. And they go up to 100 depending on kind of like, so really quite good contexts, much more than we could do before. Yeah, and with a few tricks, you can get them even further. But everybody gets this, that this is kind of like a language model. Like, as a language model, I just train it to predict the next word. As a part of speech tagger, I would need label training data. I would need, like, I don't know, a couple of 10,000 example sentences with part of speech tags done by humans. Yeah, but here for language model, it's just next word prediction. It's autocomplete. What you have on your phone, your mobile phone, when you type a text, it has a neural language model in there. It just autocompletes. It makes you suggestions for spelling, next word, and stuff like this. Sometimes this can make funny mistakes. So if you don't watch it closely, like, might suggest something that's inappropriate, you send it, and you go, oh my God. But kind of like, no, but it's a language model. It's a neural language model, actually, in your phone. Okay, yeah. Ah, very good. Okay. Yeah, thanks for that. The question is the bias unit here. So the neural networks that I've shown you did not have a bias unit. Okay. But traditionally, like when neural networks were first developed, this bias unit is a neuron that has a fixed output. And it's used to shift the nonlinearity left or right. Okay. Technically, you can compile away the bias term into a neuron that is always on, and you just learn the weight for this. And that's why in some more recent presentations of neural networks, you just don't mention the bias term. It would just be kind of like, it would be neuron 0 with always output of 1, and the weight would be weight 0. So you start your summation not weight 1 to weight n, but weight 0 to weight n, and then you have the bias term. Yeah, but it's a good question. Very, very observant. Yeah, thanks for that. Okay, yeah. So, and again, you can mathematically describe this, the function that is computed by such a recurrent neural network. So it's a function of the previous history. Yeah, that's the whole maths. That's the previous history, the h minus 1. So you're now at hi minus 1, you're now at hi, whatever, kind of like the, okay, and you combine the word embedding of the current word at state I with the previous history. That should be the embedding of the word, and then you combine them by a nonlinear function. And that's what you, yeah. In abstract terms, that's what the fella does. It's, I mean, it's if you're not steeped in the maths, it's easy to lose how beautifully simple all of this is. Yeah, it really is. It's quite amazing. I mean, like, the people that invented this is, yeah, wow. Okay, so here's an example, just an example to illustrate the differences between the count-based and the neural ones. So let's just assume that this sentence does not never occur on the internet. So Schnauzer is one of these little doggies, like I think some terrier, and they have and let's just assume we don't have the pink Schnauzer. Never, it probably exists, but you could change the sentence into something less likely. So if you have a bigram approximation, a count-based language models, okay, the probability of conditional probability of Schnauzer following pink would be 0 because you've never seen it on the web. That means the whole probability is, it just falls on its face. Okay, but a neural network, no problem. As long as it's seen the word embeddings for pink and Schnauzer. Yeah, and actually, I'm not sure whether this is the next slide. There's something kind of like that I haven't told you. Modern neural networks and modern language models don't compute with words. They only make you believe that they're computing with words. They're computing with subword encodings. And subword encodings are just chunks of words that are automatically broken up. And it's nothing to do with morphology. So, I mean, linguistics, you have kind of like, you have prefixes, you've got suffixes, you've got inflectional morphology, derivational morphology. For complex languages, you have infixing, for example. So the umlauts in Deutsch are an example of that, where you actually change something in the middle of the word, and other morphologies are even more amazing and crazy, but these are engineers, you know, and making a morphology for a language is really, actually a morphology, if you're really strong and good, you can do it exhaustively with rules for almost any language. It's one of the few things. Grammar, no. But morphology, finite state morphologies. And you know, people have done this like, I don't know, for 30, 40 years or something like that, but you need a bunch of PhD students, and if the PhD students that did this, if they go, then yeah, not good. But what they do is with subword encoding is, so initially what they say is kind of like, you know, the only words that we have are the symbols of the language, the alphabet. So the characters, uppercase, lowercase, the kind of like, you know, minus, plus, forward slash, backward slash, the numbers 0 to 1 or something like this, okay? And these symbols are the basics of our vocabulary. So this might be 100 symbols. Yeah, uppercase, lowercase, and all the print symbols that you have, kind of like in, you know, with the accents, accent graphs, and depending on the language and stuff like this, okay? And with that, you can model anything with just the characters. You know, if you have like, you know, if you have embeddings for all the characters, you can model desoxyribonucleic acid. You might. Does anybody know what that is? Probably do. Yeah, but it's not very desoxyribonucleic acid. Yeah, DNA, RNA, stuff like that. Yeah. So it's a word that's not very common and stuff. But if you have good embeddings for the characters, kind of like, you know, yeah, you can do anything. But they don't stop with the characters. What they do is kind of like they look at all the words, okay, in all the text that you have. And then they say kind of like, which two characters in this gigabytes of text, which two characters co-occur in the same sequence the most often? Yeah? And then what they take is they take those two characters and melt them together and give them a new symbol. It's actually from coding, kind of like, you know, if you want to make, yeah, so give it a new symbol, okay? And so everywhere you find those two characters, you put in the new symbol and the new code. Like, you know? And that means kind of like you have only one code where there was two before in all these positions. And then you recursively do this again. You say, then what's the next two characters that are most often together in the words in this data? And one of these may now be the new one. And you fuse them again. And if you do this 20,000 times or 50,000 times or something like this, you will actually find the most frequent words, okay? And lots of fragments, like two characters, 3, 4, 5, and stuff like this. And then before you process the natural language, but the point is finite. The dictionary is then finite, kind of like, you know, you can do anything. And any word that you've never seen before can just be broken down into, if the worst comes to the words, the character embeddings, and you've learned those as well. Okay, so with those 50,000 symbols now, you can do anything. And that's what they do. So they take the input text, they chop up the input text like that, they train everything like this. They make the predictions like that. Also, a large language model does that. And then just for us, kind of like it glues the stuff together and pretends, oh, I've actually computed with words. It doesn't. Yeah, question. Oh, it's usually kind of like you decide as an engineer. So kind of like if you have a lot of capacity in your network, you might go up to 50,000. But because you still have, you have all the fragments, and you at the basic level, you just have the initial characters. Okay, and usually they don't use the characters, but they just use the, I don't know, the code underlying these characters. That also can make the models massively multilingual, because you know you don't even look at the characters anymore, because if like the Chinese completely different from the typography, but you just look at the coding symbols, and that's how you represent your text. And you do then these subword encodings on these guys, and that makes the system potentially multilingual, because it's not biased to. You know, it doesn't have the Latin alphabet. It doesn't have the. Yeah, does everybody with me? But that's under the hood, kind of like it's not. Okay. Yeah, and then you know you can do like, you know, we're talking about these RNNs, these recurrent neural networks, and I said that they can also do mappings between arbitrary length input to arbitrary length output. One place where you need this is in machine translation. And here, for example, is such an RNN for machine translation. And it's again by a colleague from Stanford. It's German English machine translation, and translates echt dicke Kiste into awesome sauce. Kind of like, that's like, when in the US and you like some awesome sauce, kind of like, that's really cool. And in German you would say, oh, echt dicke Kiste. And yeah, and this is a recurrent neural network, kind of like, and this recurrent neural network has two components. There's an encoder and has a decoder. And the encoder reads in the sequence of word embeddings and computes a hidden representation for each one of them. So initially it's empty, then you've got this word in there, you compute a new one that records this context, you interpret dicke in the context of echt. You have a new context representation H3, a new vector that represents that. You interpret the context of Kiste, then the word Kiste in that context. Then you get a context here, this one here, H4, that is usually called, what do we call that? I'm getting tired. It's the context variable. So this vector here summarizes everything you need about the input to be translated. Okay. And you then hand this over to a decoder recurrent neural network, and that decoder recurrent neural network from this vector here has learned to generate the translation. And the way it's generated that is just because in the training you've given pairs by text. German sentence, English translation. German sentence, English translation. 10 million of those. Backprop. It learns these representations that are useful for translation. Because that's what it's learned. And it kind of like, because do you remember these start of sentence symbols and the end of sentence symbols? Yeah, they're in the training data. So each pair starts with starting sentence, end of sentence symbol, and each output sentence the same. And this fella just stops generating when he sees end of sentence. And this fella here just stops kind of like, encoding when it sees end of sentence, and just hands over to the decoder. You've trained him in parallel. Do you see how stunningly simple all of this is at the level of at the conceptual level, and how similar like a language model, machine translation, what have you? So that's just a conditional probability. It's what's the conditional probability of that English sentence given that German? It's really just a language model. And if you think, some of you might remember statistical machine translation that we used to do until about 10, 15 years ago or something like that. Statistical machine translation, yeah, how complicated it was, how much machinery we need to have, how many component models and stuff like this. And computational linguistics was generally like that. So no matter what we did, we had a horrendous pipeline of different processing things and put them all together and make them compatible and stuff like this. No, completely different way of looking at things here. Yeah, that's the bottleneck. Here, kind of like, because all the information has to go from the encoder to the decoder in translation. All the information has to go through that hidden state here, the H4. That's called the context variable, or the hidden state. That fella here that turns. Oh. And because of this context variable, kind of like, so now we come, maybe I do one more important concept with you. I think people are fading, and I'm kind of like fading a little bit. I do one more important context, and that is something that is called kind of like, but also it's called attention. So attention. Have anybody heard that term in neural networks? And yeah, okay. Right. Okay. So let me explain attention, because that's another. So I've given you a couple of key ingredients why this stuff is so powerful and so different from all the stuff that we did before. And all of this is useful actually in like philosophy and stuff like that, because you can do lots of research with the data and things. So attention is the following. So here we have an encoder-decoder system, so two RNNs. And about 10 years ago, around 2014, 15, a little bit longer, this was the bee's knees in natural language processing. So the Swiss Army knife. Everything we did was with RNNs, LSTMs, encoder-decoder systems in natural language processing, kind of like, But they have a problem. And the problem is that actually, when the context gets longer and longer, they get a bit hazy. Same about us. So when the input sentence was like 50 words, the beginning of the sentence was not so present in that bottleneck anymore, and because that's just the vector, kind of like, and the vector is more kind of like informed by the things that it's seen more recently. So the last 25 words are just more prominent, kind of like, like that. Yeah? Okay. And that had the following effect here. And you can see that over here. So in this graph, so this is for machine translation. And what people did here, this is the Baranau et al. Paper, actually the first paper that introduced attention in machine translation, neural machine translations. So here they plotted the length of sentences, machine translation sentences. Okay, so here you have sentences 10 words long, 20, 30, 40, 50, 60 words long. Yeah, okay. And the systems that I showed you before, because they tended to get a bit like fluffy about longer context, kind of like, they performed well. See those two graphs here, those two, up to sentences for about 20 to 30 words. Okay, and after that they got really bad. And actually the competitor, the classical statistical machine translation systems were better on longer sentences. Actually, the first company that used neural machine translation was not a US company, was Baidu in China. And what they did, they didn't invent it. I mean, it was really invented in the US, but they were the first to put it up for commercial use. And what they did is, like, all sentences below 12 or 15 words, they sent to the neural system, and everything that was longer to the statistical system. Like, because at the time that was state of the art, like we couldn't really do this for long sentences, kind of like, and it's partly because of that bottleneck, because in this encoder decoder architecture, which you need for translation, source language, target language, everything has to flow through this. So this representation, whatever that vector is, has to capture all of that, kind of like, and if this gets really long, that's not as good as it should be. Okay, and attention is a way of addressing this in a really smart way, so that you don't have this one context variable, but for each output that you generate, each word in the output, you look afresh at the input, and you look at what's really important for that particular output word, what's really important for that particular output word. And this is what human translators do. Kind of like, they don't just go from back to right and then have an abstract representation. If you do eye tracking, you can see that they look back on different portions of the source sentence for generating the target sentence. And let me now explain this attention to you, because you may have heard about the title of the transformer paper. The transformer paper is what the architecture of the large, pretty much. And the title of that paper is "Attention is All You Need." And that is a pun on a Beatles song. And the Beatles song is, does anybody know that? Is "Love is All You Need." Kind of like, so engineers, yeah. Attention is all you need, kind of like, And that's actually one of the most cited papers in natural language processing and machine learning. It's cited more than 200,000 times. Yeah, so the H-score for that is probably like, all of my university plus our local university here. It's incredible, yeah. And for a reason, and we're working up to that. So, but it was introduced, attention was introduced by Baranau in the context of RNNs and LSTMs. Okay, so what they did is the following, and let me try to talk you through this. This is a little bit, it's not hard, but if you get this, would be really cool. Okay, so this is an RNN, recurrent neural network, encoder decoder neural machine translation system. Yeah. So this fella here is the encoder. That fella here is the decoder. Yeah, you've seen that before. Kind of like, and normally they're connected. I would take the hidden state here. I would take that hidden state, and I would pipe it in there, and then he would generate, And that single hidden state has to encode all the information that the system learned about the input to be translated. Yeah, you with me? Do you remember that thing that went from here to there? Yeah, I showed you. That's the context variable. It goes from the encoder to the decoder. And that hidden representation, this vector here, is it. Okay? All right. So normally, that vector from here, the final state of the encoder, a recurrent neural network, goes into the decoder. But that's not what it does here. Okay? What it does here is different. Here, assume that the decoder somehow has already decoded the first word in the target of the translation. Yeah. Yeah. Echt dicke Kiste. What was it? Secret sauce or something like that, you know? Awesome sauce. Yeah. Awesome sauce. Thanks for that. So already, yeah. Okay. And then kind of like, you know, the decoder hidden state is now a hidden representation of what has been translated, the word has been generated, plus kind of like the input representation that is supposed to be translated, because they're connected like this. And in the decoder, the hidden states represent what has to be translated, what has already been translated, and so on at each stage. You know, instead of getting new input words, it's generating words, and it's recording that. In the update, it's recording that it is generated. Yeah, with me? Okay. But now what I do is I take that hidden state here that records that I've generated awesome. Okay. And I take this and pipe it back to look at all my input hidden states, H1, H2, H3, H4. Okay? And I compare this hidden state that tells me what to do next in the decoder with all the input hidden states. And by comparing this, I just take these two vectors. I take that vector and this vector, and I multiply them. Okay? And the more similar the vectors, the higher is that number. You know, if two vectors are upon like that, the result of the multiplication is what? 0. They're very similar. It's a high number. If opposite, it's minus something. Yeah? Okay. So I just multiply this vector, the hidden state, with that vector here that is recording the next thing to do. Okay. I multiply them, you know, with this hidden state, with that hidden state, with that hidden state, and with that one. Okay. And I get 4 numbers. Okay. And the number here that is biggest shows me which one of these hidden states is the most relevant for the next job to be done. Okay. I just take these 4 numbers, I send them through a softmax. A softmax is another nonlinearity that takes any string of numbers, any vector of numbers, and turns them into probabilities. Okay. Big number, higher probability, low number, lower probability. And then I take each one of these original hidden state representations, I multiply them by their corresponding probabilities, which are computed from comparing the job to be done with the information that I have in the encoder. And then I sum over them according to their probabilities. So I don't throw anything away, but this one here, you know, is much more important to the current job. That's why he's got a big line than that one. But I'm forgetting none of them. And that means at this stage, I completely reweigh all the information dynamically. And I use that, and that's the attention bit, together with the original hidden vector here, and it can now generate better. And I generate a new hidden state vector in the decoder, which now records that I've already translated the first word, second word, and this is what I'm supposed to be translating. I take this one, pipe him back, compare him with each of the hidden states over here, by just multiplying the vectors. I get 4 numbers here. The higher the number, the more relevant. That's just technical, turns these numbers into probabilities. And then each probability, I reweigh each of these representations, add them together according to their probabilities, take the now most important thing for the next word to be translated, you know, but, you know, I'm still looking at the other words, pipe that here and generate the next output. And that is just so F word amazing. Kind of like, you know, yeah. Can you see that? That I don't have a bottleneck anymore. I just at each state, and this is what humans do. You know, we look at kind of like, you know, we translate the first couple of words and then go back to another part of the sentence, translate a little bit, go back, and we look at these words, but also a little bit at those words. Yeah. So that's attention. And if you do attention, like in machine translation, you can much better work with the contexts, with longer contexts, because kind of like you just relook at all the dynamically. And if you do that, kind of like you see that graph up here, that's the system trained with attention, you know. And this was the first paper, kind of like, you know, you have to, I mean, to you, it's, you're young. So kind of like you didn't really, most of you probably don't know how awful sometimes machine translation was. Statistical machine translation was amazing, but also sometimes really, really awful. But of course, it was big technology that all the big companies had heavily invested in, like Google, you know, statistical machine translation, Microsoft, like, you know, all Yandex, a Russian company at the time, also Also in China. So I know the chap who took statistical machine translation to China and introduced it in China. And of course there was resistance to the new stuff. And this paper was the first one that showed you can translate better and you can get the same quality on the long sentences. And that was the big breakthrough. And it was using that attention. And attention is the core component in the transformer. Kind of like, it's an architecture, it's another neural architecture that really builds on this notion of attention. There's no recurrence anymore, because that's the final thing that I'm going to do now today, is the recurrence bit. Let me just go back here just to motivate this. A simple example, you see this. Yeah, that one here. The recurrent architectures are inherently sequential. Kind of like, for example, to put that word in, you have to compute this. Okay. To put that word in, you have to compute all of that. Okay. And so theoretically, your backprop has to happen at every stage. And it's called backprop in time. And it's really, really sequential. I mean, you can do all the matrix multiplications in parallel, but you first have to compute this, the error, backprop, and then compute that, error, backprop. And because the further you go, like, all the errors that happen here, they depend on this, on that, on this, on that, on this, on that. You see that? Yeah. And that is sort of like, it's not easy to train. It's computationally expensive because it's inherently sequential. Yeah. Apart from the individual matrix multiplication, of course, you can parallelize those. Everybody gets that? You see the time step after time step, next word, new context, next word, new context. And that's what you also have to do in the learning, in the backprop. And that can be a real pain, because you have like exploding gradients, vanishing gradients. The gradients, remember that they tell you about the direction and the size of the error. And you use these gradients in order to know how much to update the weights, or each one of them. You take the gradient of the loss with respect to each one of them. Okay. And if you have this backpropagation in time, it's a real pig. It's hard to train. You have to be very smart about the gradients, that they don't vanish, that they don't explode, and stuff like that. There's technology, I mean, really smart technology, but ideally you would like to have something that is at least as performant as these recurrent neural networks, and that are much easier parallelizable. And that was the motivation for the transformer paper, for attention is all you need. And that's what we're going to start with tomorrow. What's the time now? Yeah, 10 to 5. Yeah, it's good time. Okay, let's stop here. Any questions? It's like there's a saying, like, too much of a good thing. No, sorry, yeah. Yeah, they do compared to the RNNs at the time. Yeah, I mean, even though it's a good question. So in some sense, these RNNs are memory efficient, because the neural network that you see unrolled here, this one, that one, that one, that one, that one, is just this one. So the number of parameters is actually quite low, because you have these guys and they're used everywhere and trained everywhere, but it's the same parameters. Okay. So in terms of parameters, an RNN is more lightweight than transformer. Transformer tend to have many more parameters, but the complexity comes in training, because like as you learn, this is your first output, so something may have gone wrong. So you have to backprop here, you update. Then something goes wrong here. That error depends on this fella, on that fella, on this fella, and on that fella. You have to backprop again. Okay, then you update, you do this fella here. If there's an error here, it depends on these weights, on that fella, on this input, on this history, on that one, on this one, on that one, on this one. It doesn't depend on the output. Yeah. And that's backpropagation in time, like roughly. And that's the pain. Okay, because in order to compute that error here, you've done this one here. In order to compute that one, you have to have done this one, those representations, yeah, kind of like, yeah, and that's a pain. What you'd really like is kind of like to just plonk it in, have the thing look in parallel at all the words at any time, and still have encoder, decoder, It's not easy. I mean, if you haven't seen how they did it, it's very hard to get the idea. But yeah, it's an amazing paper, and we're gonna talk about that because that's the foundation technology. So this one is kind of like, I mean, I'm not sure this one could be scaled to the web scale data that large language models use nowadays. Transformers were very much built for that, for scalability. That you can train these fellas and you can make them really, really big, and you can train them on like half the web, all the web, and stuff like that. And with these guys, no, no. And there's also clever ways of transformers to enable them to deal with contexts of hundreds, thousands of words, tens of thousands of words. You know, even though the full attention complexity, the interesting ways of taming that. Yeah, but I think the important thing about transformers to remember is, first of all, like a little bit about the architecture I'm going to talk about next time, and it's really enabled the scaling, you know, to the massive large language models that we have nowadays. Okay, you can also make the transformer multimodal, so it can also do something with pictures and stuff like that. There are ways of that. It's called the vision transformers. They have similar architecture. Yeah. Okay. Yeah, yeah, yeah. Because I mean, kind of like, you know, if you think about it, if you have a very simple language model, kind of like, let's say a count-based language model, and you train it on a baby, you know, baby is da, 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 ba, 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 or something like this. You know, if you just use unigram probabilities, that language model can generate output that is never seen in training. You know, because in training it just seen like ba, 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 da, da, or Kraftwerk, you know, fahren, 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 Autoweiser. Yeah. And it can train things that were never in the training data. And that's, you know, it's either a great discovery if it's something that we haven't seen, or it's a hallucination, but it's the same, exactly the same mechanism. It just goes according to its probabilities, you know. And with these large language models, also, I mean, these large language models are not only language models. So you pre-train them as language models, just next word prediction. So that way they learn about language, grammar, and culture, and all that kind of stuff, kind of like almost as side products. But then there's a second phase of training, which is called fine-tuning, or some other names. And that's where you train the system to be a good chat partner, good at question answering, because like on the web, a lot of data is not question answering, you know, it's just text, kind of like, you know, it's just not a good conversational. You really tire very quickly, kind of like, you know, they're not good, you know, they sound like Wikipedia or kind of like, you know, and dodgy stuff, you know, because they change. There's, you know, a large part of the web is pornography, and yeah, the train on everything. And if such a system, if you provoke it, it will just happily just dump it on you. It will be racist, misogynist, anything you want it to be, because it's seen anything. You know, but it's our stuff. I mean, we have produced this, you know. But there's then a second phase in training, like after that language model training, which is called sort of like fine-tuning, or that makes it a chat partner. It also aligns it with human expectations. It's supposed to be friendly, supposed not to, you know, fascist, or, you know, easily provoked. But it's a question, right? You know, some people do training material. You know, go to China. The Chinese language model asked about Tiananmen Square. Didn't happen. West. Ask the Chinese model about COVID. He's lost. In China, there is actually a coup at the government. Not have that and like that. This and the efficient Chinese thing. Yeah. Because I can't talk about it. Yeah, let's talk about something else. Because non-issue thing, but it doesn't have like such an action. It's really hard. It's when the election came up in the US. I asked before the election, I asked Google, who won the last election? It was Biden. Biden got the popular vote. Actually got the majority, like, you know, where you can't vote once, and you got the majority in the electoral college. So you got both. and Google refused to answer. Said, but no, I'm sorry, I can't answer this. I'm so trained about political kind of like. I asked ChatGPT, it had to be said that in the White House, there's a list of all the official results of all American elections since the independence. But no, ChatGPT said Biden, blah blah blah. Then I asked Google, like, so don't you trust this document here on the? He said, sorry, I can't, and you see, really scared. Google is scared by. So it's not just China, but China is absolutely. Anyways, yeah. Okay.
Okay, thank you very much. So tomorrow, enter.
Yeah. It'll be the exam then.